8. Right, first question. We gave you a code here, so we ask you to examine the Vhdr code of it's a D flip-flop, and then discuss in details discuss the design style used here. I think this one is easy, right? So the design style used here. What is the design style used? Are you connected or?
Yeah, it's a behavior.
Yeah, strange. I'm not getting answers. Good, excellent. So it's behavioral. We are using a process, and inside process we are using a sequential statement. So this is behavioral. Good. When are the statements inside this process are executed?
When there is an event on clock or clear.
Excellent. So we have clock and clear. So whenever there is an event on one of them or both, then this process will be triggered and it will be executed from here to the end and then back, and then it keeps waiting. Is the clear here? So as you can see, this D flip-flop has a clear. So basically we have D, we have clock, and it has a clear here, C, or CLR, we call it CLR. So is this clear here synchronous or asynchronous? And explain why. Is the clear synchronous or asynchronous from the code?
I think asynchronous and doesn't depend on the clock.
Excellent. Good. Do you see we are checking the clear here before the clock? So it's not controlled by the clock. So we are not checking this clear after making sure that there is a rising edge. We are checking this outside. So the clock, it's like the priority is for the clear, which means it's not controlled by the clock, so it is asynchronous. Good. Now we ask you here in the next question to rewrite the process. So we ask you just to rewrite this process in the above VHDL code to replace the type of the clear identified in 2 with its opposite. So if we identify it as asynchronous, so now we need to write the code assuming that this one is synchronous. I think we did something similar in the lecture. So basically we just we start with so this will be an if, and this will be moved inside. So if when we say it's synchronous, this means we need to wait for the rising edge first of the clock. So which means we need to check the clock first. So if we have a rising edge, then we check the clear, and then if there is a clear, then the output should be 0. If not, then D is equal, Q is equal D. And that's it. So we just start with this one first, and then we move this part inside the if statement of the clock, checking the clock. I think we did something similar in the lecture. Just to switch to the solution, just to show you what I mean. This one. So we start with the clock. So if clock, and then we check the clear, else we have the Q is equal D. Right. Next question. 3 instances of the D flip-flop described using the VHDL code in this figure here. So we have 3 instances of this used in this circuit. So we have D, we have clock, we have Q, and we have clear. Right? So we use them in this circuit. The first question is, and this is a 3-bit shift register. So the circuit is 3-bit shift register. So we ask you to write basically the VHDL code to describe this using components. So first we ask you to write the entity and then the architecture. Right. So for the entity, what should we have in the entity for this circuit?
The inputs are clock, clear, and serial data in as STD logic, I think. And the output will be parallel data out.
Yeah, the type is what?
STD logic 2 down to 0, I think.
STD logic vector, right?
Yeah.
So STD logic vector. Inputs, so good, excellent. So inputs, we have serial data in, I can just call it SD. And then we have clock, I can call it CLK or clock or whatever. And then we have clear, CLR. Those are inputs. Outputs, we have just one. I can call it parallel or PD. And this one, as you said, is 3 bits, as you can see. Right? And then all what we need to do next, of course, we go to the architecture. We declare this as a component. And then what do we need to do next? The port mapping, right? I'm just trying to copy the circuit so you can see it in the, if it will be easy to see it or not. Just to be clear when we do the port mapping so you can understand what right. So switch to the solution. I just updated the file, but it's on OneDrive, so I don't think it's been updated here. Didn't update. Okay, it's fine. We can work with the this one. So we'll start with the port mapping. I think you know how to declare the components, yeah? So I'm not going to repeat this. So components, we just copy this, paste, and that's it. So we already have the VHDL code for the component. We didn't ask you to write it again. It's already here. So we have D, CLK, CLR, and Q in this order. So we need to follow this order. D, CLK, clear, is it like that, yeah? D, clock, clear, and Q. So this is the order in the component. And then we have SD, clock. I can name this clock just to avoid confusion with this one here. And then I can name this just C for clear. Those are in the entity of the circuit. Do you follow, yeah? And then we have the output PD. We need, some internal signals, right? So this is an internal signal. This is another one, and this one can be an internal signal as well. So I can use this Q1, Q2, Q3. So I need to declare them as signal, Q1, Q2, Q3 signals. And then I'll just go one by one. So we'll take the first one. So how did we call this? DFF. So the component should be DFF, port map. And then what do we have first? Starting with this first one. So what do we have?
The first one is D1 connected to SD.
So we put SD here. And then we have clock. Next, right? Is clock connected to clock. So clock is in all of them. So we should have all of them. Clear is the same. So C, we call it C here. C is connected to all of them. So clock and C should be in all of them in the same position. And then Q1. And I will repeat this again for the second one. And then I will have Q1 instead of D2. So it's connected to D. And then clock. And then C. And then Q2. And then I can have same here. Q2. And then clock. And then C. And then Q3. Here, because it's directly connected to data, parallel data, I can even use, instead of Q3, I can use parallel data 0. Both of them are correct. So one of them. But of course, I need to connect Q1 and Q2 to the other 2 bits of the parallel data out. So there is still something missing. So if I use Q3 here, I can just write at the end PD is equal, and then I will just use the concatenation. Q3 is the first bit, so Q3 will be here, Q2, Q1. And that's it. Those 3 bits grouped together will give me PD. And by the way, this signal here, I declared it as, I can declare it as STD logic vector. So I can name it Q signal or whatever, because I already have Q, yeah? So if I name this Q signal and it will be STD logic vector, same size as PD, then I can use here Q signal 0, Q signal 2, 1, and then Q signal 2. And then at the end, I will just do PD is equal Q signal because it's 2 bits, it's 3 bits, it's like the same size. And so all solutions are correct. And they will give me the same circuit. Is this clear? So if I switch to the solution, this is what I was talking about. The architecture is here as SD, clock, clear, and PD. And then here I used the components declaration, and then I used the signal here of same size or as PD. And then here I worked with signal 0, signal 1, and signal 2. So I use them here. And then at the end, I'll just do PD is equal Q signal. And this line is very important. If you don't put it, then it's a disaster. I mean, nothing will work. You will not get an output. Is this clear?
Yeah.
Okay, excellent. Next question. So we gave you this circuit here, and we told you, okay, what should be the figure 2 shows a sequential circuit, and those are JK flip-flops, yeah, connected this way. So we ask you to copy this figure here, the waveform here, and to use it to show what will be the outputs Q0, Q1, Q2, and then this one. So we have, we want you to show me Q0, Q1, Q2, and then combine together what will be the output. So all flip-flops are positive edge triggered and are initially reset. So all flip-flops start from 0. And this should be very simple. So what do you think for Q0? What do we get? So we start with 0. And then first rising edge. What do we get?
One is a toggle, so we get Q bar, which is 1.
It's a toggle. Good, excellent. So we are toggling in all of them. Do you see here? All of them are connected to 1. So it's always a toggle. So it goes to 1. Like this. And then goes to 0. Then goes to 1. And then 0. I'm doing this just to show you, to show you that at this time it's 1, and then it goes to 0. At this time is 0, and then it goes to 1. And then like that, yeah? I think it's very simple, this circuit. And then next, Q1. For Q1, look. The clock of next one is connected to Q0 bar. So Q0 bar is the opposite of this one, of Q0, right? So when we have 0, now we work with the rising edges, right, of the clock. So if I have a rising edge in Q0, so Q0 now, or Q0 bar, is the clock of the next one. You follow me, yeah? If I have a rising edge Q0, this means it's a falling edge in Q bar, Q0 bar. I'm going to draw Q0 bar. This is Q0 bar, right? Q0 bar. Now I need to draw Q1. How do we get Q1? Q1 is the same as what we gave. How did we get Q0? But the clock here is Q0 bar. So this is the clock. This is the clock for Q1. So where are the rising edges? The rising edges are here. Right? So those are the rising edges. And then we start with 0. Q1 starts with 0, then it goes to 1, and then it goes to 0, and then goes to 1, then goes to 0, and that's it. Is this clear? Do you follow me? Yeah?
Yeah.
And I will do the same for Q2. Now I will do Q2. For Q2, Q1 bar is the clock. And this is Q1. So which means if I have a rising edge here, it means it's a falling edge in Q1 bar. So those will be the edges for me to consider the edges in Q1 are the rising edges in Q1 bar. So the last flip-flop should work on those edges here. So if I draw it again, we start with 0, stays 0, and then goes to 1 here. I have, now if you can see, I have 0, 1, sorry, 0, 0. I will delete this one so we don't need it. So Q0 is the green one, Q1 is the red one, and Q2 is the black one here. So we'll have 0, 0, 0, 1, 0, 0, 0, 1, 0, right? 1, 1, 0, 0, 0, 1, 1, 0, 1, 0, 1, 1, and then 1, 1, 1. So what do you think is the last output? Oh, the output. The output here, I will get 0 here. Of course, I need to represent it using this, this shape, yeah? But I will just push the values here. So I will get 0. Then I will get, just use a different color. 1, this is 1 in decimal, right? Then I will get 2. Then I will get 3. Then I will get 4. This is 5. This is 6. And this is 7. So what does this circuit do basically? Is a counter. This is a counter that counts up. It's a 3-bit counter. So with 3 bits, we go 0, 0, 0, 0, 1, 0, 1, 0. Every clock cycle, we increment. We go by 1. And this is what we got. Is this clear? So if I show you the waveform, this is what I was explaining. So this is what I get. So 0, sorry. 0, 0, 0, 0, 0, 1, 0, 1, 1. Oh, sorry. 0, 1, 0, and then 0, 1, 1. And then 1, 0, 0, 1, 0, 1, 1, 1, 0, and then 1, 1, 1. I put them inside in decimal. Right. This is probably a solution. Is this clear?
Yes.
And the circuit is very simple. I mean, we are toggling. Each time we toggle, now is the difference from one to the other and to the next one is just the clock, which signal is used for the clock. So we are not using the same clock for all of them. Do you see here for the shift register is the same clock for all of them. In this circuit, in this counter, is not the same clock. So we have this is the original clock. And then for the next stage, we use the Q bar for the next clock. And then for the third stage, we use the Q bar from the previous one, and so on. So if I want to do a 4-bit counter, I will just add another one here, and I will just take this to the clock. And that's it. And then I will add this to the output. And I will get a 4-bit counter. And then if you draw the waveforms, you will get counting 0, 1 until 4-bit until 15. And then it goes back to 0. Now if I extend this more, the next value will be 0. So it goes to maximum 7 and then 0, 1, and then it repeats again every clock cycle. Once you stop the clock, if there is no clock, it will remain as the last value. So if it stays at 1, it stops 1, keeps displaying 1. Right. I think the time is almost over, so I prefer to stop here. We have one question left here in this exercise. Is actually 2 questions. So the next question is to write the code to describe a JK flip-flop, and then we use it as a component to describe this counter, this circuit. So we'll do them next session, inshallah. And then we have another question about the simulation test bench. I think we stopped this question. We did part A. I think we are done with this. Right. I think we found out that the circuit is a counter, right? So it says it does a counting. 0, 1, 2, 3 up to 7 because it has 3 outputs. So we found that it does 0, 0, 0, 0, 1, 0, 0, 0, 1, 0 until 1, 1, 1 and then back. Every clock cycle it increments by just drawing the waveforms, and this is what we found out. Yeah. Now next question is to write the Vhdr code to describe the JK flip-flop. We did examples with the flip-flop, so now it's about the JK flip-flop. So you know the truth table for the JK, you know how does it work. So we have 3 inputs, we have J, K, and clock, and then we have 2 outputs, Q0 and Q0 bar. And then we will have different cases based on J and K. Of course, on every rising edge, we need to check J and K, similarly to what we did with the flip-flop. Every rising edge, we check, of course, if this is positive edge trigger. So, and this is what we said in this question. So it's positive edge trigger. Every rising edge, we need to check J and K, and based on this, we update the Q and Q bar. So again, it will be if statement inside the process. And so we'll switch to the solution. Just to go to the, so this is the code. So start with the entity, step by step. So we have 3 inputs, clock, J and K. We have 2 outputs. I named one is NQ and the other one is Q. And then I used signal here. I called it JK. This is one solution, by the way. You can have all different solutions. So you can have, here I use the case statement. You can use if statements if you want. And then the condition could be J and K. So you check J and K. So what I want to do here, I want to concatenate J and K together. So I can have 0, 0, 0, 1, 1, 0, or 1, 1. So I will read the inputs, individual inputs J and K. I will put them together, and then my test will be based on this JK. Is it 0, 0, is it 0, 1, 1, 0, or 1, 1? You can do it separate if you want, yeah, but this is one solution. So JK, and I used another signal, I called it state, and this is for the output. Again, I'm using this for the output for the reason of not being able to use, you know, I cannot do Q is equal, Q bar and Q is equal not Q. I cannot do this because Q is an output and Q is an output. So this will give me an error. So what I'm going to do, I will use state, a signal, or you can call it whatever you want, yeah, or Q signal or whatever. I called it state. And then I will work with state inside the process. And then outside the process, I will do Q is equal state and Q is equal not state. And that's it. So this is to avoid the issue of not being able to use the output on this side of the equation. So is it clear why I use this JK? I declared it as a 2-bit signal, and then I will work with it. Of course, you can work with individual J and K. I mean, and then you have them in the condition. Right. So outside the process, I started with a simple signal assignment. I used JK is equal J concatenated with K. And then inside the process, I will use this signal JK. So whenever this J and K are updated, this output JK will be updated, the signal, and then it will be updated here inside the process. So those are parallel statements. So basically, how many statements do we have here running in parallel? We have this one, we have the process, we have this statement, and we have this statement. So we have three statements, like if we consider the statement 1, statement 2, sorry, 4, statement 3, and statement 4. Those are 4 statements running in parallel. Right, of course, the main statement here is this one, the process. So we go inside the process, and of course, it will be based on the clock. This process will be executed if there is an event on the clock. So this is the first thing that we need to make sure that there is a rising edge. I used here the rising edge function. So if there is a rising edge, then I use the case statement inside the if, or you can replace this case statement with an if statement as well. If, else, if, and so on. So case statement is good here. JK, so based on the value of J and K, so if it is 1, 1, then state should be equal to not state. If it is 1, 0, then this is a set, then state should be 1. If it is 0, 1, then this is a reset, then state should be 0. When others, which means the other case, 0, 0, then state is equal state, no change. So those are basically from the truth table. This is toggle, first is toggle operation, then set, then the reset, then no change. Again, as I told you, you can replace this with an if statement. So you do if JK is equal 0, 0, then else if JK is equal 0, 1, then, and so on. So it will be replaced with an if statement. Again, this is not the only solution. Even if you don't do this statement here, the first one, the concatenation here, you can even work with if J and K is equal, or if J is equal 0 and K is equal 0, then so you can work with them as separate, ports. You don't have to concatenate them. But concatenation is a good solution here, so it makes it easy for me to use a case statement. And that's it. I mean, this is we are just following the truth table of the JK. So checking, of course, this is very important, rising edge, to check if there is a rising edge, and then the rest is just I'm following the truth table of the JK. Is this clear? So if we have if this JK was with a preset or with a clear, and then again, it will depend is it synchronous or asynchronous, then we can add them here. If it is asynchronous, we can put it outside. Let's say preset is equal, then I can use state is equal 1 if it's a preset. And then if it was synchronous, then I can have it here. I can do the test here. So it's similar to the flip-flop, what we did exactly with the flip-flop.
But doctor, if it's asynchronous, you also have to put it in the process statement, yeah?
Yes, you're right. If it is asynchronous, then I have to include it here, the P, because it will depend on it as well. The process will not be triggered only by the clock, it will be triggered as well with the P, because this P will affect the output regardless of the clock or the other input. Yes, you are right. So we did this anyway for the flip-flop. So it's exactly the same solution. Right. So this is for the JK. And then the next question is just to use this as a component. I think we did similar question before with the flip-flop. So we use this as a component to implement this circuit. So we just need to do the port mapping. So for example, the first one, you know now how to declare a component. So for the first one, we need to do port map, and then J is connected to 1. So I think for all of them, the J and K will be 1. And then K is 1. And then the clock is CLK, is the clock of the circuit, right? And then if we call it CLK in our port map, in our entity. And then we have, here I don't need signals for Q0, Q1, and Q3, because we are not using them. So they go directly to the output. We are not using them again as input for the next one. So if we are not using them, then we can just use the output itself by using, you know, if it's called output, I can use O0, O1, and O2. Those are the separate bits. So the Q0 is connected to O0. The Q1 is connected to O1, and the Q2 is connected to O2. So I can just use them here. Is this clear? And even if you declare them as signals, you can work with signals. But at the end, you need to assign the signals to the final output, which is fine again. This is another solution. So if I switch to the main solution, this is what I was talking about basically. So here I called it clock in for my circuit. So remember, this is the circuit. So what are the inputs and the outputs of this circuit? This is the circuit that we want to implement. So the only input that it has is the clock, right? So if I consider this as a black box, so the only input is the clock. This is 1, is constant. And then we have the output. One output, one input. I call this CLK in, and we have one output. So CLK in, and then one output. I called it O. And for O, it's 3 bits, so I need to declare it as STD logic vector, right? 2 down to 0. And then, you know this, I need to declare the component. And then I used, we have some internal signals, as you can see here, for the not Q. I should have put the, so those are the internal signals that I'm using. So this is 1, not Q is an output, and then it's connected to the next clock. Same here. Is this clear? So those are internal signals that I declared. What is NQ0? I didn't see the third one. Sorry, NQ2. This one, it's unconnected. So we have the last one is not connected. So if I want to have a 4-bit, then I will connect it to the next one. So this needs to be declared as well as an internal signal. And I showed you this for the port mapping. I showed you the first one. So we have clock in. I started with clock in because in in the code I started here with clock J and K, NQ and Q. So we have to follow this order: clock J and K, and then NQ and Q. And then so clock in is connected to the clock 1 1, and then NQ0, and then Q0. Here, this is the final output, and that's it. I do the same for the remaining 2 flip-flops. Clock for the next flip-flop, as I showed you in the figure, so we take it from NQ of the previous one. So this is why we have NQ0 here. So the NQ0 of the previous one is connected to the clock of the next one, and NQ1 is connected to the clock of the third one, and so on. So if I have another one, fourth one, then I will use this NQ2 and I will connect it to the clock, to the fourth one, and so on. Is this clear?
Yes, no.
Okay, good. We did many examples now with the component, so I hope it's clear to everybody. Right, back to the, I think, last question. So this is the, yeah, we are done with this question. Last one is related to simulation. So if we give you this circuit, I think you should know the answer to this. What is the design style used here?
Data flow.
Data flow.
Data flow, good. Because we are using just two simple signal assignments. So if I draw this circuit here, what will be the circuit? So I have, so E is a signal, so I have A, B, and C. A, B, C are inputs. So A is equal, oh sorry, E is equal A XOR B. So this is XOR. I will guess the E, and then I will just take it with C and do an AND. And then I will get my D. So this is basically the circuit that we are doing. Right. This is general question. What does a VHDL test bench contain? We said it contains the unit under test. So we use it as a component plus the test cases or the stimuli. This is what we have in a test bench. Right, now in order to simulate the logic function in this figure, so we want to simulate this one, which is basically the circuit. VHDL test bench is required, right? So we ask you to write the components declaration that we need to use in this VHDL test bench, and to write the component instantiation. And then, so basically we are asking you to write the test bench, and then the VHDL test bench, the full VHDL test bench. And then using the wait and assertion statement, write the process part of the VHDL test bench that produces the waveforms shown in this figure here. So we want you to generate those waveforms and report an error when the output is wrong for the following cases. So we want to check at this time, 50 nanosecond. We want to check at this time, 100 nanosecond. Here after 100, this is so first 50 nanosecond, then after 100 nanosecond. So basically here, we check here, we check here, we check as well after 100 here, and then here at the end. So we check at this time. So we ask you to simulate this. So we have three inputs, A, B, and C. And then we need to use the assert. And then do the, so for the component declaration, I think it's easy, right? We just copy this, because this is what we want to simulate. And then we just replace this, the name with component and component here. All right, we don't change anything. We don't change the name of the port. We don't change the order. Right, so this is what we do first. In the, of course, if you are asked to write the full test bench, you start with an empty entity, and then we go to the architecture. So basically here, what we are doing here is just the architecture part. Starting from the component declaration, and then we need to do the component instantiation or the port mapping for this unit under test, right? To do this, we need to declare signals with these names, A, B, and C, right? A, B, and C, STD logic, as they are. and D, sorry, as well, because we have D as an output. So all ports, as I said, should be declared as signals. And then we do the port mapping. We just put the names as they are. Port map A, B, C, D. And that's it. So this should be the case for any test bench, according to the template, right? Just to show you the solution. So this is the component. So components declaration. And then the port mapping. Here I didn't put them in one line, but of course you can put them in one line, yeah? A is connected to signal A, B is connected to signal B, C is connected to signal C, and D is connected to signal D. Of course, you can remove this, because those are optional. So you can just put A, B, C, and D. How does the compiler know this? Because it knows that the first port is A, the second port is B, the third port from the entity or the components declaration. It has it here. So it knows what is the first one, it knows what is the second one, it knows what is the third one, and what is the fourth one. So this is optional. Right. Is this clear? So those are parts in the test bench. We put them here in separate questions, but those are parts of the same test bench. And then we go to the last part where we ask you to generate those test cases here. I can do 3 separate processes, one for A, one for B, one for C, as we did in the example that I showed you, the AND gate, right? If you remember in the lecture. So process 1, process 2, process 3. Or I can do all in one process. And because I want to use the assert, I can insert the assert here. So for example, I will have one process, begin, and then we do A is equal 0, B is equal 0, right, for the first 50 seconds, and C is equal 1. C is 1 here, right? And then I can do wait for 50 nanoseconds. And then I can insert the assert here. Assert, what should be the condition here? It should be on D, right? The output is D. Assert D equal what? I need to go back to my code, right? Or to my circuit. So what should be D here? If I have 0, 0, 1. 0,
Should be
0,
1.
1. Should be 1. This is an AND gate. I have this C is 1. Then this should be 1. Good. So then it should be 1. I need to put 1 here. Report. So if it is not 1, then I will report an error. There is an error in the first case, or whatever. You can write whatever you want. And severity is error. Yes.
Wouldn't the XOR gate give you 0, so the AND gate will finally be 0?
Sorry. This is yeah, this is an AND gate. Yeah. So the XOR gate will give me what here? If this
0.
was an OR, yeah, then the XOR gate will give me 0. So this is 0. Yes. Sorry, yeah, I thought it's like an OR gate, and yeah, so it's 1. This is 1, and then 0, 1, and 0 is 0. So I should put 0 here. Report. Anyway, you understand the concept. This is what we need to do for all cases. And then I need to go to this one. Next one. A is equal 0, B is equal 1, C is equal 0. Wait for 100 nanoseconds. So we split it like this. So 0, 0, 1, 0, 1, 0, and then we have it here. 1, 0, 1, and then 1, 1, 1. Those are the cases that I want to test. I think for this case it's clear. So now if I have 0 here, then this is 0, right? It's an AND gate. So I will repeat this and putting the values for the new values 0, 1, 0, and the assert, it will stay the same, and so on. So I will repeat this until I finish the 4 cases. So I can show you the full code here. And that's what we are saying, yeah? So this is the first case. This is the second case. So D is 0 here, D is 0 here. This is the third case. So D is 1. 1 XOR 0 will give me 1, and then C is 1, so it gives me 1. And the last one, it should be 0. And that's it. So I can put them all in one process. Now, can you change this code and put 3 processes? What are the changes that I need to do? So I want you to write again, to repeat this, or to solve it using 3 processes. So one process to generate A, one process to generate B, and one process to generate C. And of course, the assert, you can put it in one of them. And it's better for it to be within A, according to the waveforms that we have. I don't know if you understand what I mean.
Doctor, so it would be the same thing, but we take out B and C.
Yeah.
And then for the process for B and C, we take it as a copy paste from this, and we remove the assert statement, and we remove AC for B. For C, we remove AB and the assert statement.
That's good, excellent. I think it's, yeah, you are right. So now if I go to the question, just delete this. The assert, I said it's better to be with A, but I think it's better to be with B. Why? Because it's the B that is changing at those times, right? 50, and then it's changing here, and then it's changing here. So it's better to use. So for A, I can just do A is equal 0. Wait for how many? 50, 150. No second. And then I will do A is equal 1. Wait. So that's it. This is what I need to do to generate A. For B is the same code that we wrote, right? So B is 0, wait for 50, and then B is 1, wait for 100, and then B is 0, wait for 100, and then B is 1, and then I can finish with wait. And then C, I can do C is equal 1, wait for 50, and then C is equal 0, wait for 100, and then C is equal 1, and then I can do wait. And that's it. I can finish with, can keep them, you know, the last values will stay 1, 1, 1 forever. So if I go back to the code, now, so basically I can delete A, I can delete C from here, I can delete A from here, I can delete C from here, I can delete A from here, and C from here. And then I will push the 2 processes that I was talking about. So the asserts can stay here because this will run in parallel. Yeah, so we will be checking at this time 50, and then 100, and then 100, and then 50. And then I can have a process for A, begin. A is equal 0, wait for 150, then a second, and then I can do A is 1, wait. Here I can finish it as well with wait. I don't need to repeat the and. So this is for A, process A, and then I can have another process for C. So C is 0, wait for 50, and then C is 1, wait for 100, and then C is, oh sorry, we start C with 1, and then it goes to 0, and then C is 1, and then wait. Of course, you can specify the last time if you want, but wait is enough here. And this is for D. So those three processes will run in parallel. Assert can go only in one of them. I don't need to have it in all, because they will run in parallel, and we will be checking at this time. So because they are running in parallel at this time, at 50 nanoseconds, we know that A is 0, and we know that C is 1. Right? Because those two processes are running in parallel. And so on. So you can do it all in one, or you can have three separate processes. And remember, we are considering only the inputs. We don't care about the outputs. Of course, we care about the outputs when we check, when we use assert. But if I don't use assert, you will not see D in my test bench. The output D. We will not see it if I don't use the assert. Is this clear? Right. So that's it for this tutorial.